It's well known that when two planes intersect, they will contain a common line. Now, let us ask a question. Is the same true in four-dimensional space? Is it true that two-dimensional planes in R4 contain a common line if they intersect? Of course, two planes may not intersect because they may, for example, be parallel. Now, but so if we have two intersecting two-dimensional planes in R4, so is it true that they will contain a common line? So here I suggest that you pause this video, then write down the answer on a piece of paper, and then resume. The answer to this question is the following: that in R4, two-dimensional planes may intersect at a single point. So one should picture something like this. So we may have two-dimensional planes that will have just a single point of intersection. Now, so this all sounds extremely counterintuitive. And so this is a place where our brain will try to deceive us. And so actually this only speaks very good about our brain. So that our brain has innate intuition about three-dimensional space. But unfortunately, it doesn't give us sometimes good advice about R4. But here we need to resort to what we learn in linear algebra course. All right, so let me convince you that this is something that can happen in the four-dimensional space. All right, so let's consider R4. Right, so here in R4 we have four coordinate axes. Right, so we have X, Y, Z, and W. And so the vectors in R4 will have, of course, four components. Right? Now, let us think, how would the XY plane look like? So let's consider an XY plane in R4. So which vectors will form XY plane? Well, XY plane is formed by vectors that will have arbitrary X and Y coordinates and 0 Z and W coordinates. So this means that the vectors in XY plane have the following structure: something here, something in the second component, and then 0 in Z component and 0 in W component. So this is how XY plane looks like. Now, how about ZW plane? So the vectors in ZW plane will have 0 components in first and second position, and then arbitrary Z component, and then arbitrary W component. Now, let us look, what's the intersection of these two planes? So we are going to intersect XY plane with ZW plane. Now, in the intersection, we will have vectors that satisfy both patterns. So, but from the first pattern, we see that a vector in the intersection should have 0 third and fourth components. And from ZW plane, we see that any vector that belongs to ZW plane must have 0 first and second component. So what we see is that this intersection consists of a single vector 0, 0, 0, 0. Right? So this is the only vector that conforms the first pattern and the second pattern. And so this is the only point of intersection of these two-dimensional planes. And so this means that this xy plane and zw plane, when intersect in R4, so the only point of intersection is going to be the origin, just like here. In this lecture, we will study the question of intersection of subspaces in Rn and see how we can address this problem not from the geometric but from algebraic point of view, from the point of view of linear algebra. So suppose a subspace U in Rn is given by a system of linear equations Ax is equal to 0. So this means that vectors in U are those vectors that satisfy the system of linear equations. So then, what can we say about dimension of this subspace? So we claim that the dimension of a subspace is given by n minus rank of a matrix A. So how do we know this? So this is a consequence. So this follows from this rank nullity theorem. So, which we considered in the previous lecture, that said that rank of A plus nullity of A is equal to the number of columns of A, right? And so what do we have here? So here we have a system of linear equations that determines a subspace U. So this means that, well, what we say here, so this means that U is null space of A. That's what we say here, right? And when we say that this is a system of linear equations in Rn, so this means that X here belongs to Rn. So this means that X has n components. And what we know is that the columns of the matrix of A correspond to unknowns. So this implies that A has n columns, right? And so then what we take this rank nullity formula, and we can express nullity as the number of columns minus the rank. And the number of columns is equal to the dimension of the ambient space. So what we get is we get this formula that if we obtain a subspace as in Rn as a solution space of a system of linear equations, and because it's in Rn, so this system must have n variables, then dimension of this subspace is determined by the rank of a matrix. So it's n minus the rank of a matrix. Now let's look at like very basic example. So suppose U is given as a solution set of a single non-zero linear equation in Rn. So this means that we have one equation. So a1 x1 plus an xn is equal to 0. And not all a coefficients, so the left-hand side is not 0. Now, what can we say about dimension of U? So here, so the matrix A consists of a single row, A1 up to AN. And this row is non-zero. So rank of A is equal to 1. And then by this formula, we get that dimension of this subspace is n minus 1. So if we have a single equation in n-dimensional space, then it determines n minus 1 dimensional subspace. So this is what we get from this theorem. And so this is something that is quite natural, right? So if we have 5-dimensional space and we impose one linear constraint on it, then the set of solutions will be 4-dimensional. Let us try to understand how come in 3-dimensional space 2 planes must contain a line of intersection if they intersect, and in a 4-dimensional space 2 planes can intersect at a point. Now, let us start with the situation of R3. So, a 2-dimensional plane is given by a single equation. So, one linear equation in R3 defines a 2-dimensional plane. Well, this is what we said here, right? So if we have one equation in Rn, then this determines the subspace of dimension n minus 1. Right? So now, so if we have 2 planes, so this means that we have 2 linear equations in R3. And what does it mean that we look for intersection? So when we look for intersection, so this means that we join 2 equations in a system. Now, so one 2-dimensional plane in R3 is given by one equation. So then intersection of two-dimensional planes is given by a system of 2 equations, right? So now we have 2 equations in R3. Now, what can we say about the rank of such a system? So we can see that so if a system has 2 equations, then rank of this system cannot exceed 2, right? So because rank is the dimension of the row space, and here we have 2 rows, so this means that the dimension of a row space cannot exceed 2. And so then this tells us that dimension of the intersection, right, of U, so U, this is intersection of 2 planes, is going to be greater or equal to n, which is, so we are in R3, so this is 3 minus 2. And so this is 1. And this tells us that the dimension of the intersection has dimension greater or equal to 1. And so this means that intersection of any 2 planes in R3 must contain a line, which is a 1-dimensional subspace. Now, let us look at the same problem in R4. So here, so let V and W be 2 two-dimensional subspaces in R4. And so let's imagine that these subspaces are given as solution sets of systems of linear equations. So given by systems AX is equal to 0 and BX is equal to 0 respectively. So V is given as a solution set of a system AX is equal to 0 and W is given as a solution set of BX is equal to 0. Now, what can we say about matrices A and B? Right? So what we can say here is, so by our formula here, so we have, so dimension of V is equal to n minus rank of A. So here dimension of V is equal to 2, right? So we said that we have a two-dimensional subspace, and n is equal to 4. So this is the dimension of the ambient space. So from here, it follows that rank of A must be equal to 2, right? And the same applies for rank of B. So this tells us that to define a two-dimensional plane in R4, we need at least two equations, right? And so what really is important is not the number of equations that defines this subspace, but the rank of the corresponding matrix. So the rank of the corresponding matrix must be 2. Well, in row echelon form, this matrix will contain two non-zero equations. So that's the point, right? So we have a matrix A and matrix B of this type. Now, so which system will give us the intersection? So intersection of V with W is given by a joint system, right? So where we say AX is equal to 0 and BX is equal to 0. Now, what is the joint matrix for this system of linear equations? Well, it will be a matrix that contains matrix A on the top and matrix B at the bottom, right? So now, what can we say about the rank of such a matrix? Right? So we put one rank 2 matrix on the top and another rank 2 matrix at the bottom. And so what we can see is that the maximum possible rank of this matrix is going to be 4. Right? So it very well could be that you have two equations in A, two equations in B, and all together, so we get a matrix of rank 4. Right? And so if U is the intersection, so if we say that so V and W has intersection of U, then what we get is that dimension of U is equal to 4 minus, so this 4 is the dimension of the ambient space, minus the rank of this joint matrix. And what we can see is that this is only greater or equal to 0. So here we were able to prove that dimension of the intersection is greater or equal to 1. Whereas for two planes in 4-dimensional space, the same inequality that we get will be that it's only greater or equal to 0. And if the rank of this joint matrix is 4, which very well can be, then we get that dimension of U could be 0. And so a 0-dimensional subspace is a point. So this tells us that so two-dimensional planes in R4 may intersect at a point. So this is the geometric conclusion of this algebraic calculation. So let us state a proposition describing rank of such a joint matrix. So proposition. So if we join two systems of homogeneous linear equations, AX is equal to 0 and BX is equal to 0. Well, this is in Rn, right? So this meaning that X here belongs to Rn. Then, so we can say that the rank of the joint system A and B is greater or equal to the maximum of rank of A and rank of B, and is less or equal to minimum of the sum rank of A plus rank of B and n. All right, let's prove this fact. So we recall what's the rank of a matrix. So rank of A is equal to dimension, for example, of a row space of A. And so rank of B is also the dimension of the row space of B, and the rank of this joint matrix is the dimension of the row space of the joint matrix, right? But what we see is that this joint matrix contains all rows of A, right? So from here we see that row space of the joint matrix contains the row space of A. So this means that the row space of A is a subspace in the row space of the joint matrix. And from here we get inequality for dimensions. So this means that dimension of the row space of the joint matrix is greater or equal than dimension of the row space of A. And but by definition, dimension of the row space is the rank. So this tells us that the rank of the joint matrix is greater or equal to the rank of matrix A. But likewise, instead of matrix A, we could have used matrix B. So this means that we also get that rank of the joint matrix is greater or equal to the rank of B. But if it's greater or equal to this number and this number, then of course it follows that it's greater or equal to the maximum of these two numbers. So we get the first inequality of this theorem. Now let's introduce notations. So let's say that rank of A is equal to P and rank of B is equal to Q. Now let's recall what's a dimension of a space. So the dimension of a space by definition is the number of vectors in its bases. Now, what's the row space of a matrix? A row space of a matrix is the span of the rows of this matrix, say R1 by Rm. So let's recall a lemma that we had that said that if we have a finite set of vectors, then this set will contain a linearly independent subset with the same span as the original set of vectors. Now, this linearly independent subset of the rows of the matrix A that will have the same span as the set of all rows, so that will be precisely the basis of the row space of A, right? So let's just say it again. So if we take a linearly independent subset of the set of rows of a matrix, then this linearly independent subset will become automatically a basis of the row space of A, because it will have the same span as the original set of rows and will be linearly independent. So this means that there exists a subset of P rows, right? So where P is the rank, that, so of A, that span the row space of A. So we can choose, so if rank of A is equal to P, so this means that we can choose P rows of A that will span row space of A. So these P rows will be linearly independent. In the same way, we get that since rank of B is equal to Q, so this tells us that there exists a subset of Q rows of B that span the whole row space of the matrix B. So taking the union, so we take these P basis rows of the row space of A and Q basis rows of the row space of B, we get P plus Q rows of this joint matrix AB that span its row space. Right? So because we have P rows that span the row space of A and Q rows that span the row space of B, so then together these P plus Q rows will span the row space of the joint matrix. It doesn't mean that these P plus Q rows be linearly independent, right? So this very well could be that joining two linearly independent subsets, we get possibly a linearly dependent subset. But what is for sure we know is that these two spanning sets will span together the row space of the joint matrix. So now we get that the row space of this matrix is spanned by P plus Q vectors, or P plus Q rows. So from here it follows that dimension of the row space of this matrix is less or equal to P plus Q. Right? So this follows from a theorem that we proved, that we said that if we have a vector space that's spanned by n vectors, then any larger set of vectors, right, so any n plus 1 vectors will be linearly dependent. So this means that if we take a basis in the space which is spanned by n vectors, then the number of vectors in the basis will be less or equal to n, because a basis consists of linearly independent vectors, and any set of vectors that in size exceeds n is automatically linearly dependent. So this means that if we have a space that's spanned by P plus Q rows, then this means that dimension of this space is less or equal to P plus Q. And what's the dimension of the row space? Dimension of the row space is the rank. So from here we get that the rank of this matrix is less or equal to P plus Q, but P is rank of A and Q is the rank of B. And so of course, so we also have the inequality that rank of this joint matrix is less or equal to n, because in addition for the rank to be the dimension of the row space, it's also the dimension of the column space. And this matrix has n columns, right? So this means that this matrix, the column space of this matrix is spanned by n vectors. And so this means that the rank of this matrix is less or equal to the number of columns, n. And so if we have two inequalities, that this rank is less or equal to the sum and it's less or equal to n, then of course this rank will be less or equal to the minimum of these two numbers. And so what we get is that the rank of the joint matrix is between the maximum of the two ranks and the minimum of the sum of the ranks and the n, so the dimension of the ambient space. Now, as an exercise, let's look at the following problem. So what are possible dimensions of intersection of a six-dimensional subspace U and a seven-dimensional subspace V in R9. Right, so we take a 9-dimensional space and we take a 6-dimensional subspace and a 7-dimensional subspace, and we intersect them. And we ask what are possible dimensions of intersection. So for example, could the intersection of a 6-dimensional and a 7-dimensional subspace in R9 be a plane that is 2-dimensional? Now, to solve this problem, so we look at systems of linear equations that determine these subspaces. So let U be given by AX equals 0 and V given by BX is equal to 0. Now, what can we say about the ranks of A and B? So we use our rank dimension formula. So from here it follows that rank of A is equal to 9 minus dimension of U. All right, so 9 because 9 is the dimension of the ambient space. So it's the number of columns in the matrix A. And so this is equal to 3. Right, so to get a 6-dimensional subspace in R9, we need to impose a matrix of rank 3. And from here we get that rank of B is equal to 9 minus dimension of V. So that is equal to 2. So B must be a matrix of rank 2. And so then intersection so U intersected with V is given by the joint matrix, so AB. Now, what is the rank of this joint matrix? So what we see is that the rank of the joint matrix is greater or equal to the maximum of rank of A and rank of B, and is less or equal to minimum of the sum, so rank of A plus rank of B, and n, well, which is 9 in this case. And so what we get is that the rank of this matrix is going to be, well, the maximum of 2 and 3 is equal to 3. And here we get 5, 2 plus 3, and 9. So the minimum is equal to 5. So this tells us that the rank of the joint matrix could have values 3, 4, and 5. Right? And so if rank of the joint matrix is equal to 3, so this tells us that dimension of the intersection is well, again, we use this rank dimension formula. It's 9 minus 3, so this will be 6. So if this rank is equal to 4, so then this tells us that dimension of intersection is equal to 5. And if rank is equal to 5, so this tells us that dimension of the intersection is equal to 4. So this tells us that in R9, so possible dimensions of intersection of a 6-dimensional subspace and a 7-dimensional subspace is either 6, 5, or 4. Well, and clearly the case 6, for example, so this means that this 7-dimensional subspace contains this 6-dimensional subspace, right? So this is the only case when the intersection will have dimension 6. And so if this 7-dimensional subspace does not contain this 6-dimensional subspace, then dimensions of intersections could be 5 or 4, but cannot be 2, right? So this tells us that we cannot have a plane, a 2-dimensional plane of intersection of these two subspaces in R9. So far here we discussed only homogeneous systems of linear equations and thus subspaces, right? So, but of course we could also have these shifted subspaces, so say lines and planes and high dimensional generalizations that do not pass through the origin. So these will correspond to systems of linear equations that have non-zero right-hand side. And it is slightly easier to discuss the homogeneous case because we know that in homogeneous case, a system is always consistent. So because we always have a solution x is equal to 0. Any subspace passes through the origin. And so this means that any two subspaces intersect at least at the origin. But let's think what will happen if we take non-homogeneous systems instead. And now we get the possibility of inconsistent systems. And thus, we could have two these shifted subspaces that do not intersect. Let's begin with a theorem describing the connection between consistency of a system of linear equations and its rank. So we have a theorem that says that a system of linear equations ax equals b is consistent if and only if the rank of the augmented matrix so AB is equal to the rank of the coefficient matrix. A. Right, so here we take the coefficient matrix A, or we take the augmented matrix where we add to the coefficient matrix the right-hand side column. So if the rank does not change when we add this extra column, then the system is consistent. And if the rank increases, then the system is not consistent. So to prove this theorem, so we recall that AX is B is consistent if and only if there is no pivot in the right-hand side column. And so what's the rank of a matrix? well, rank of a matrix is the dimension of the row space or column space, but the way how we calculate it, so the rank of a matrix is equal to the number of pivots in row echelon form of A. And so if there is no pivot in a right-hand side column of row echelon form of the augmented matrix AB. So this really means that the number of pivots of A, so number of pivots of A, of row echelon form of A, is equal to the number of pivots of row echelon form of the augmented matrix AB. And so this number of pivots is, so this happens if and only if rank of AB is equal to rank of A. And so what we obtain is that exactly the claim of this theorem. So that the system is consistent if and only if rank of augmented matrix is equal to the rank of the coefficient matrix. So now let us slightly generalize the previous problem. So let us look at so what are possible intersections of 6-dimensional and 7-dimensional this let's call them hyperplanes in R9, so not necessarily passing through the origin. Right, so we have like 0, and here we have one subspace, and here we could possibly have another subspace, and we're interested in finding out how can we describe this intersection. And so here, so these hyperplanes are now given by non-homogeneous equations. So AX equals, say, B, and BX is equal to C, right? And well, of course, these have to be consistent because otherwise they will not describe these hyperplanes. And so what we see is that rank of A here, because of consistency, is equal to rank of AB. And so this rank must be equal to 3, right? And so rank of B is going to be equal to 2. And so then, so for the intersection, so we join these two systems into one big system. So AX is equal to B and BX is equal to C. So, and here we could have two cases. So we could have that, so this is inconsistent. So it could happen that we join two consistent systems and we get inconsistent systems. So this means that two hyperplanes do not intersect, right? So for example, like in R3, we could have two lines that cross and do not intersect. Or, so this can be a consistent system. So this means that we could have, say, P some particular solution. So, but then, So we had another theorem that said that if we have a non-homogeneous system with a particular solution P, then so the general solution is equal to P plus so general solution of the system AX equals 0 and BX is equal to 0 of the corresponding homogeneous system. And here we already know what are possible answers. So here we know that so this general solution is a subspace of dimension 4, 5, or 6. Right? And so this means that if these two hyperplanes intersect, then the intersection is going to be still a hyperplane of dimension 4, 5, and 6. Right? So this hyperplane is a shifted subspace. So we have some point P, and so then we shift the subspace by this point. Right? So basically, so the answer for non-homogeneous systems is exactly the same, or almost exactly the same, as for homogeneous system. Only there is one extra possibility that these two subspaces may be non-intersecting at all. Right? So for non-homogeneous, for these hyperplanes or non-homogeneous systems, so there is an additional possible answer. So it will be a hyperplane of dimension 4, 5, or 6, or it could be the intersection could be empty.